Okay. Cabbage? No, thank you.
Pizza, yes.
Not that Irish. All right, so let's do this first question. What are we looking for in this problem here? This first question up here, what are we trying to find?
How much heat was added?
How much heat was added? So the unit of the thing we're looking for is what?
Calories.
Calories. Okay. So in these questions, what's important is these are change questions, right? I want to know how much heat was added to this piece of aluminum. Okay, fine. Do I care what the initial temperature is? Do I care what the final temperature is? I don't care what either of those things are. I really don't. I only care what the change in those things are. So when I'm putting my railroad track together, I am not putting in 3 degrees Celsius, and I'm not putting in 110 degrees Celsius. I only care that there is a change. Because when I add heat to something that's already 3 degrees Celsius, the thing's temperature goes up, whether it started at 3 degrees Celsius or whether it started at 300 degrees Celsius. Its temp's still going to go up the exact same amount. So do I care? So what do I do with those two temperature numbers? So when you see a problem like this, just immediately subtract the two of them off. So in the second problem, you can just do the exact same thing, do some subtraction immediately. So in this one, the only thing I really care about is the temperature of this piece of aluminum went up 107 degrees. Are we good with that? So my my delta T for this is temperature final minus temperature initial, and this is 110 degrees Celsius minus 3 degrees Celsius, so I'm looking at 107. I'm looking at 107 degrees Celsius. Okay, so I need calories, and the only thing that I have calories in up here is my my specific heat number. So I'm going to go ahead and start off by writing 0.22 calories per gram degree C. Great, I've got the unit that I want, and it's in the position that I want it to be in, and so I just need to get rid of the calories in the degree C. So let's go ahead and get rid of the degree C. We already know what number we need to use because we just calculated as 107. So why am I going to write this 107 here? Yeah, so this one on the bottom gets canceled out with this one on the top. Okay, great. So now I only need to get rid of that grams number, and the grams number we've got is 75. So I'm going to take 75 grams here, and I'm going to cancel that out right there. And the only number I've got left is, or the only unit I've got left is calories. So I punch this into the calculator. Let's see. Can I do that? I think I have a calculator here. Where did I put it? Huh. It's next to the, there's a camera?
About the trophy. Second one to the right. The green.
It's green? Green. All right, green's good. Ah, that's lame. All right, let's do this. I am certain there's a calculator here somewhere. I want just that right, there we go. That's what I'm looking for. So I'm going to take 0.22 and I'm going to multiply it by 107, and then I'm going to multiply it by 75, and I'm going to get 1765.5. So how many sig figs do I have? Does everybody see 2? Because it's 3.0, right? Okay. So what should I put? 1800. So, oops. 1800 calories. Okay. All right, so for this next one, I told you it was tricky. I would have suggested if somebody had asked me to draw something like this, so you could think about the problem. So there's a couple of tricky things with this. One of the tricky things is, what's the final temperature of the lead? It's 22 degrees. How do I know it's 22 degrees? because I had 11-degree water, and the water's temp with the lead in it went up to 22 degrees. How come the lead's temp didn't go up to, or the water's temperature did not go up to 23 degrees?
Because you had to balance the level out, because the cold, the water went into the lead, and the heat of the lead went into the water.
There's no such thing as cold.
Well, the less heat.
So nothing went into the lead. No cold went into the lead. What came out of the lead?
Heat.
Energy came out, heat came out of it, but you didn't send some arbitrary something or other called cold into it. So heat came out of it, but when did heat stop coming out of the lead?
At 22.
When the two of them had the exact same amount of temperature, right? Which is average kinetic energy. So when their energies equaled each other, that's when they stopped exchanging energy. Does that make sense? Okay, so I've got 22-degree lead, and I can either use the equation, use railroad track, use just thinking about this problem. It doesn't really matter. I'm going to put the equation up here because I think some of you wanted to see the equation. So I'm going to put lead Q equals MC temperature final minus temperature initial. All right, so in this problem, what do we know about the lead?
You know how big it is?
We know this thing's mass. It was given. What else do we know?
You know its final temp.
We know its final temperature because we just figured that out at 22 degrees. What else do we know? Or what else can you find out?
The calories that,
You can go look up its specific heat, right? The specific heat of lead is just a known value. Okay, so you've got 3 of the 5 pieces to this. We don't have the temperature final or initial because that's what we're looking for in this problem, right? So we're trying to find that temperature initial. So what we would like to know is what is the change in energy for the lead? So we can calculate that out by figuring out what the change of energy is for the water. So my water is the exact same question or equation. So for the water, I know all of these pieces. I know the temperature initial was given. I know the temperature final it was given, so I have the change. The specific heat of water is 1, I know that. And the mass of the water was given at 175. So I can calculate the entire energy input for this water. So let's go ahead and do that. So I've got, what do I got? 1 calorie per gram degree C, because I want calories in the numerator. Then I'm going to throw 175 grams in the numerator, so my grams cancel. And then I'm going to put 11 degrees Celsius here because my 22 final minus my 11 initial gives me 11 change. And so then my degrees Celsius is here. And is it 1925?
Yeah.
Great. That is the amount of energy that the water absorbed. What does that also tell us?
that's how much the lead gave off.
That's how much the lead gave up. So this Q value right here goes right here with 1 change. What's the change? It's a negative value. Okay. So I can write negative 1925 calories equals 75 grams times 0.038 calories per gram degree C times 20 degrees Celsius, or sorry, 22 degrees Celsius minus temperature initial. This is as hard as the algebra gets in this class. We're looking for that temperature initial. So this doesn't work out for us if we do not have this negative sign here. We get a number that's like 44 degrees off. Okay, so so I'll move the 75 over by dividing, I'll move the 0.038 over by dividing, and then I can add a temperature initial to both sides, and I can subtract off whatever this thing is. So let me. So what I end up with is the temperature initial is equal to negative 1925 calories divided by 75 grams divided by 0.0388 calories per gram degree C, and then I'm going to add 22 degrees Celsius to that. And so the grams cancel out, the calories cancel out, and I only have degrees C left with this. I'm pretty sure this number works out to be like 675 degrees C, and if I add the 22 to that, I get 697 degrees C. And there's the last little bit of trickiness to this problem. How many sig figs do you have? 2, right? So I got to get rid of the 7, but if I get rid of the 7, I have to round the 9 up, right, to a 10, which gives me 700. So is this my answer?
That's not one.
That only is demonstrating a single significant figure. I can't put the decimal place after the second 0 because if I do, that says 3 sig figs. And I can't put after the first 0 because then it's 70 and not 700. So my only option would be 7.0 times 10 to the second degree C. Because then I have the 7 and the 0 telling me 2 sig figs, and 100 times 7 is 700. Everybody happy with that one?
So again, not being math smart at all, the only thing I didn't add was the 22 Celsius, so I came up with 680. But I got to it without negative anything.
It was just luck. It was, you made 2 mistakes and they
Okay.
canceled each other out. Or you were just thinking about the problem correctly, because if you didn't include the negative sign, then you should have gotten a negative degrees C. But does that make any sense?
No.
It doesn't make any sense for 2 reasons. One, negative 600 degrees Celsius is significantly below absolute 0, so that's out. Also, if I put something with a negative degree C in water, the temp doesn't go up 11 degrees Celsius if I start at 11. So
And my railroad was flipped, I think.
that's probably...
No, I started with a flipped, I started with a flipped specific heat on lead, and I worked my way from there. I just started plugging in numbers.
As long as you got all the units to cancel out except for the degrees C, you'll be fine. And then you have to think about the problem being a high number temperature-wise instead of a low number temperature-wise.
I think for me, it's just math with dividing negative, because it keeps, I don't remember math, but it keeps flipping signs if you're dealing with negative numbers, doesn't it?
You only have 1 negative.
I see and understand that. I'm just
You'll get more practice.
sucking that.
I'm a little confused why, I mean, it makes sense, but I didn't think that I would have gotten that without you telling me that it's negative 1925 in the next equation.
Okay, so the lead, you okay with me saying the lead was hot?
Yeah,
How do you know that?
because
It raised the temperature of water. So if I'm raising the temperature of water, sure, the temperature is going up, but what's temperature a measure of?
Energy.
Energy. The actual temperature is a measure, in our definition, it's a measure of the average kinetic energy of a substance. That's what we said the definition was. So if something's temperature is going up, its energy is going up. And for substances, when their temperature goes up, what did we say we should actually be thinking about is happening to the molecules? They're moving faster. Okay, so I have this hot chunk of lead, and the atoms inside the lead, they're moving really fast, right? Why? Because they're hot. I take them and I put them into water molecules, and what happens to the water molecules? They start moving faster. What happens to the lead's molecule, atoms? They slow down.
So it just lost.
Whatever the water took in, the lead must have given it away. And it's got to be the exact same value. It's just the sign has to be opposite.
So that's why you're saying a negative 1925, because it has to give that away.
It gave that away for sure. Its temp went down, and if its temperature goes down, that means its average kinetic energy went down. So energy, which is measured in calories, must have been given away. So it lost, so that's why it's negative.
I didn't use the negative, but I still got the same answer. So why are you saying I wouldn't have the correct answer? I think my equation,
Math magic.
It just kind of happened. Because you guys were looking.
I took the.
Two mistakes, possibly.
I took the
That's the nice thing about
1925
negative, right?
over the here and this. I had this.
That's just nauseous.
Okay, so
Well, I did this
There's
equation.
That's what
Well,
this doesn't matter if
okay.
it's positive or negative.
It
In
would-
this
it would be
specific
that.
instance, if I
Because
take
that's
that,
what's
divide it by that, divide it by that, I'm still going with this.
That's the only unit that's left over. Which, so I just spread it across
So-
them all, and I
If I
took
just,
that.
That's not the right answer.
This by that.
What are you pointing at right now?
Well, no, wait, but I didn't do it all in one equation like you did. And then I knew that if.
Okay, right there, stop. The reason that you got it right is because you said to yourself, I know that this temperature went down. Because that 675 that you have right there, what does that actually represent?
Okay, but this, it represents, and what I wrote next to it is, the temperature needed to have 1,925 calories transferred to the water. But then I also know that for a reaction to stop, they had to be at equal temperatures, so then I added the 22 degrees, because that's where the water stopped.
Okay.
And then I got,
Whether it's.
the 697. And then I had a problem with the significant number.
That's a different question. Tell me what that 675 represents.
That represents, the actual temperature.
Nope.
The actual temperature that was, subtracted, basically,
The actual temperature what?
that the lead gave up,
So-
or got rid of,
It lost
yeah.
675. So
So I did it in my head, but didn't write it on.
that's
paper.
what yeah.
Gotcha, okay, but I did.
Which is
give
fine
an
because you
explanation.
understood what was going on, but
Yeah,
you're not going to be able to do that every time.
right.
It's not going to be an intuitive, this lead obviously lost temperature. It's not going to be that intuitive when you're calculating out, I don't know, milliliters of solution to inject into somebody's veins. So that should have been negative all the way through. More about this one? More? Okay, so you just went into Canada.
That's not on ours.
What?
We have what makes both the great theory and the Dalton's theory of the atom such a great move forward.
No.
Yeah.
You had that one?
Yeah, we
Yeah.
have the other.
Those aren't on yours?
No. No,
Lame.
no, we got lucky.
I know. I know, I'm like, shoot, did I not
Okay.
print out right?
Not getting a homework question isn't lucky, because that means I expected you to already see it. What's the exam gonna look like?
Just like that.
Wouldn't you like to see as many possible exam questions as you could possibly see? Yeah. Okay.
So, go ahead and show
Yeah,
us.
go do it. We'll watch. I'll watch the video.
So you drive into Washington, or you drive from Washington into Canada, and the sign displays 125. Why should you not get super excited?
Because it's.
It's in kilometers per hour, right? It's not miles per hour. So how do I convert this into what because a 66 Mustang is not going to have kilometers on the speedometer next to the miles per hour. So how do I do that? It's 125 kilometers per hour. So there are two units with this, but we don't have to worry about the hour unit because it's miles per hour too. We just need to convert that kilometers. So I'm going to go, not 1,000, I'm going to go 1 kilometer is 1,000 meters. and I'm going to go 1 meter is 100 centimeters. I'm going to go 2.54 centimeters is 1 inch. And 12 inches is 1 foot. And 5,280 feet is 1 mile. Feet are gone, inches are gone, centimeters are gone, meters are gone, and kilometers are gone. And so now I have miles per hour. And what do we got here? So 125 times 1,000 times 100 divided by 2.54 divided by 12 and divided by 5,280. What was it? 77.7. Ah. 7. Yeah. Still pretty fast, but regardless.
Could you repost this homework online?
Yeah.
Okay.
Are we good with that? Okay. Okay. So you drop your iPhone in the river. It's in a waterproof case. It was supposed to float, but it turns out it didn't float. The phone has a mass of 135 grams, and the case has a mass of 45 grams. What's the minimum volume that would allow the case to float, the case in the phone to float? No, that's the density. So what's the minimum volume you would need?
So when you add 135 and 45, and then whatever those add.
So 180, your total mass of your phone in your case is 180 grams. Great. So what volume do you need?
181.
Sure, 181 would be enough. You need to have a slightly greater volume than you do mass to get something to float. Are we okay with that? If the volume is larger than the mass, and we're talking grams and milliliters, then the thing's going to float. Somewhere in the Columbia, there is a perfectly fine iPhone S3 in a waterproof case. I'm sure it's dead, but the battery's dead, but it's sitting there. Okay, so how about this next one? What do you guys have for these two theories?
That everything is made up of mostly nothing.
True, but I don't think that's a huge jump forward for science.
That there's
And-
more than just 4 elements.
Okay, so one thing they cancel, it ruins the 4-element theory, which is good since it's not true. Yeah.
So, in continuing on with everything is nothing, now you start looking for what the nothings are. So instead of just looking at this chunk of dirt and the wind on your cheek, you're now looking for things that you can't see. You're looking for things that shouldn't exist.
Okay. You start looking.
Shouldn't they raise like questions of what is an atom made of?
Okay,
They gave rise to questions of the atom structure.
sure. So these guys didn't do, the Greeks for sure, they didn't do any atom science, correct? They just thought about it. And from the thinking about it, got other scientists to look into the problem. Like, are they right? Is there really stuff called atoms? So without these people thinking about the problem beforehand, you can't actually start doing anything. What's the first part of the scientific method?
Come up with a theory.
Come up with a problem. There's got to be a problem, and the problem is stuff made of atoms? That's our question. If you don't have a question, then you have no direction. So they put everybody on the right path, and the wrong paths were phlogiston and alchemy and the 4 elements. It got them off of those paths and onto the correct path. So we wouldn't have been looking where we were supposed to be looking if somebody hadn't thought of this in the first place. What can you say about the magnitude of the charge on a proton relative to an electron? They're equal. I'm just asking about the magnitude. They are equal to each other. And it's super important because that proton is so much bigger, massive, so much more massive than the electron, but they still completely cancel out. One proton, one electron, I put them together, and what's the charge? Neutral. It's zero. There isn't a charge. So Dalton, what's Dalton's theory about happens during a chemical reaction? Think about Legos. You can make as many things as you want with Legos because nothing happens to the Legos. And that's the deal with atoms. You make as many molecules as you want and you can take them apart and put them back together and nothing happens to the basic building blocks. So does it make sense that we call them building blocks? Because when a kid has a bunch of building blocks and he builds up a wall or a little castle out of his little wood building box, does anything happen to the blocks? No. Knocks the castle down, starts over, and builds a car. It doesn't matter. They are themselves eternal. Why is Dalton happy to know that water's formula is H2O?
The ratio is the same.
Okay, two reasons. One, it's always two H's and one O. What else?
Confirms his theory of definite proportions.
Okay, that's what this is.
Yeah.
Simple whole numbers. And the last question. Sweet. Matter is mostly empty space. Is that one on there? Cool. How about this one?
The matter that's in the atom is mostly in the nucleus.
Okay, and?
So the space between the electrons and the nucleus is mostly empty space.
Okay.
It's all more in the middle concentrated.
So the mass is concentrated down into the center. How much smaller is the center than an average atom?
Lots.
Right? 10 to the negative 15th an atom. So what's the difference between those two? I got an atom and it's 10 to the negative 10th meters across. And I got a nucleus and it's 10 to the negative 15th across. So what's the difference between those two things?
5 orders of magnitude.
Yeah, we're talking about 10. The nucleus is 10,000 times smaller than the atom as a whole. So if I'm talking about the mass of the atom, it's all tightly packed into this tiny, tiny little spot in the middle of this sphere. So there isn't just that, but that atom is bound to another atom, right? So what's the distance between this nucleus and the next nucleus? It's a long way, right? First I got to get to the edge of this atom, then I got to jump the space between the atoms, then I got to jump from the outside of that atom all the way down to the center of the nucleus in the next atom. So there are really, the actual chunks of matter are really, really far away from each other. How far is Alpha Centauri from the sun? Alpha Centauri is the next closest sun. It's a long way away. So the universe is what?
You empty space.
Mostly empty space, just like you. Okay, so you evidently have questions.